see Yuri Rostovtsev.
Recording in progress.
I don't see either, so I'll send him email right now. Just a second.
Okay, I see everyone else.
You can start anyway, yes.
Okay. Is everybody here? I don't want to start if nobody's, it's just me and you. That's all. I'm guessing probably people are still gone a little bit. I'll share my screen. I liked your background, Olga.
Mm-hmm. You can easily recognize, right?
Yeah, I can see Snowbird there.
Mm-hmm.
I'll try to keep, what I'll do, I'll try to keep everyone to time by giving a warning at 17 minutes.
Yeah, good. But still, at least 1-2 questions would be good because discussion is important. Yeah.
Yeah. So maybe I should do a 15-minute and say you have 2 minutes to finish, then we can have 3 minutes for questions.
Okay.
Well, maybe I should just ask how many people are here. How many people are here? Should I get started?
Yeah, sure.
Yeah.
Okay. So do I say that Rustem Shakhmuratov?
Yes, I am.
Okay. I saw you were next.
I'm here.
Okay, great. And okay, looks like we have a few. Okay, well, I guess I'll get started. First of all, thank Olga. Olga, I think you should be a saint of science for all the organization you do for various conferences. Thank you for putting these together. And also, I just want to say for those who are going to be speaking in this session, what I'll do is I'll give a 15-minute, I'll give at the 15-minute mark, I'll give a 2-minute warning so that you can, that'll put you at 17 minutes, and we'd like to have about 3 minutes for questions. We'll try and stick to that so that we can finish on time. Okay, and I will be a good example by doing that myself. So, okay, glad to be here and glad to participate in this. It's been a while since I've participated in LPHYS', and I'm grateful to be able to do that again. My name's John Howell. I'm at Chapman University now. I joined here about a year ago. I was at University of Rochester for 15 years and Hebrew University for 5. So my collaborators on this are Andrew Jordan, Barbara Soda at the Perimeter, and Achim Kempf also at the Perimeter Institute. Okay, so just want to make mention of a couple things. We have some positions available. We do quite a few things in both quantum and classical. We've been recently just been working on radar, And I want to talk about some of the things that we've been doing with radar and why that's interesting. And so we've gone way beyond the standard approaches to range resolution. In fact, we're about 1,000 times, roughly about 1,000 times better than standard range resolution techniques using a new set of functions that we've designed. So I'm going to go through and talk about range resolution, Rayleigh resolution, frequency versus resolution, interference, why it's bad, interference, why it's good, and then how we went beyond the standard range resolution technique. So in the Rayleigh criterion, if I have a finite aperture, for example, in a telescope, and we want to be able to resolve two distant objects, the Rayleigh criterion is dependent on the diameter of the objective. And what happens is, because you have a finite objective, you get airy disks based upon these circular apertures. And these airy disks, what happens is we can resolve Rayleigh defined resolution as when we can resolve those, the peak of one object is at the minimum of the other object. So if I have two airy disks separated by the first minima, then I have a resolution between those two things and those two objects. And so you can see that down in the bottom right-hand corner, these two objects being resolved, and the airy disk looking at that in one dimension, essentially the first order Bessel functions over in the bottom left-hand corner. And the x equals kd rho over 2f. D is the diameter. And so you can see the what we basically want to do is we want to increase that diameter as much as possible. So how do we go beyond Rayleigh? Well, recently there was some nice work started by Mankhej Singh, in which they basically showed that if they have two incoherent point sources, they can resolve these using getting down to the quantum correlation by simply decomposing these incoherent sources into modes. And so by doing a mode decomposition, they were able to get down to far below this Rayleigh criterion. So now shift over to radar. Basically, radar really started with once Maxwell completed the classical E&M theory, Hertz came along realizing what he had done and made great efforts to demonstrate what Maxwell had theorized. And when he was asked, what are all these experiments useful for? He said, nothing, I guess, which I thought was an interesting response now that our whole world seems to be defined by these things, by Maxwell's equations. And Christian Holzmeier came along a little bit while later, and realizing the importance of Hertz's work, basically made what we would call a metal detector. And he called it the telemobiloscope, but it basically was used to prevent ships colliding with each other. And he was referred to by Watson Watt as the grandfather of radar. He didn't have any ranging capabilities, but he was able to detect metal objects both above and below water, which was really important for preventing ships from colliding. And as we know, radar became incredibly valuable in World War II and became basically the first time radar was used to great effect. For example, the British staved off the Nazi Luftwaffe and basically were able to get air superiority because of it. And anyway, World War II ended up being important for radar. Now, what is radar? So if we want to think about it, it's radio detection and ranging. Basically, you're using radio waves to detect objects and to range objects. And the simplest way to get ranging information is, for example, a time of flight. You send out a pulse, you see how long it takes to return, and you can get information about it. But there are all kinds of ways of doing this. For example, FMCW, frequency modulated CW LiDAR, in which you're basically ramping up the frequency of the radar and looking at how the frequency changes as a function of time. Match filter radar, in which you're basically doing the reverse of the pulse that you send out, and you're able to pull out a signal in very low noise. But range resolution is, for example, in radar, isn't the ability at how well you can resolve distance, it's how well you can resolve two objects at a distance. So range resolution is, if I have two objects, for example, these two planes flying in formation, and one has a distance that's different from the other, then resolution is basically what would we consider, for example, the Rayleigh criterion in space, but now in time. When you can see the return pulse separated from another pulse, then you get two pulses. You can see that there are two objects out there, and you can resolve that. If you have these two planes flying right next to each other and you're not able to angularly resolve these two planes, then you get what looks like a single pulse, and you wouldn't know the difference between one or the other. Now, it's pretty obvious that if I have a pulse of length tau, these equations, this SR up here, this is the range resolution up in the upper left-hand corner, is C0 times tau over 2. The 2 basically comes from the fact that you get a round trip effect. C tau is basically just the length of the pulse in space. And so you can see if the distance between those two objects is C tau over 2, then we should be able to resolve those. But it's more general than that, because you can also send out these pulses, for example, these time varying pulses, FMCW, or time varying pulses, or these match filter pulses, and do pulse compression. And so what really matters is the inverse bandwidth. So you just take the speed of light divided by the inverse bandwidth, and that is what you would call almost the law of range resolution. That's how you can separate two objects. Now, why do we care? If we get higher resolution, we should get higher bandwidth, right? We require higher bandwidth to get higher resolution. So why do we care? If we get good range resolution at high frequencies, then why would this matter? Here's a classic example. Suppose you're trying to do some demining, and you need to be able to tell, you want to get relatively high resolution. You want to be able to tell a mine or something underneath relative to a rock or whatever. And so you want as high resolution as you possibly can get. And so you might think, well, just use high frequencies. The problem is that when you use high frequencies, you run into a resolution. When you use high frequencies, you can't probe very deep. For example, in ground penetrating radar, for example, you can get centimeter resolution at 6 gigahertz, for example, but you can only probe down a few centimeters. And you can get very deep. You can all the way go down to about 40 meters deep, but your resolution is many meters or tens of meters. So you have very, very poor resolution. So it's a trade-off. You either get good depth or you get good resolution, and you can't get it both ways using this. But it's the same is true in water, seawater, air propagation. The lower your frequency, the better the propagation. But the higher the frequency, the higher resolution, but you get poor penetration in almost every medium. Okay, so here's just a classic example. I just basically took a sync squared pulse, and I took that sync squared pulse and I separated it by going from tau equals 0, in other words, no separation, to tau equals 1, where tau is the separation by by separating it to one width. So in other words, when the first minimum, but when the separation is equal to the first minimum. And you can see that we get the Rayleigh criterion for tau equals 1 and unable to get resolution for anything less than that. Okay, now if I just look at what the sinc squared pulse is, it's the fast Fourier transform. It's a triangle function, which is exactly what we would expect. You know that a sinc pulse gives you a square in the Fourier transform, but because it's a sinc square, then you get the Fourier transform should be the convolution of the square wave of the self, giving us a triangle. So first I thought, well, how can we do better? How can we do better than range resolution? Let's use super oscillations. So super oscillations give you local frequencies that are faster than that are outside the bounds of the Fourier transform. And I thought that might be an interesting method for doing that. And I was able to see something that was interesting. I was able to get an improvement by about 30%, but it turns out someone had already done that earlier. Wang and LPHYS' had gotten 36%. I saw about the same result. And basically I was using, you can see here in this particular poll, these diagrams in the top, what I have is a Gaussian curve, which is in orange. And then what I did is I separated that Gaussian curve, and I wanted to see how much I could change it. But then I have a super oscillating term in the blue, and I was able to get the green peaks to be separated. So it showed that we could get an improvement over the standard Gaussian pulse. But I really wanted to improve this more, but I kept running into an annoying problem. And this is shown in the figure down below. In the orange, again, I have a Gaussian pulse. Then if I have two objects scattering, what happens when I add their waves? And the curve in red shows the two objects for two Gaussian scatterers. But then the blue curve is what happens for a super oscillation. But instead of shifting laterally, what it did was shift upward. And I saw thousands of these curves, and it was really annoying. But then I found out that actually could be better than super oscillations. And so it turns out to be millions of times actually better. And so there are some really interesting things here that have been done by a lot of people in using quantum techniques for example, pulse separation. This one down at the bottom here by Christine Silberhorn's group, in which they were able to achieve the quantum timing resolution. And they did basically this mode decomposition, but in time. And so we're taking on a different technique though. And let's consider these functions for a minute. So I have three functions plotted here. The C2 is just basically the sinc function as what we have. And then all of these other curves, this orange curve also has the same band limits as the blue curve. So this blue curve is just a standard sinc. It has the standard band limits. The orange curve is using band limited function theory, which is what I was using some band limited function theory and is able to make this orange curve. And then I use this green curve, and I'm going to focus on the green curve for just a minute. And I want you to notice a few things. And so let's design a function that's super sensitive to interference. Instead of worrying about interference, let's design a function that's super sensitive to interference. And so let's think about what we want. In the green curve, what I'm going to do is create regions of ultra steep interference. And so these green curves, if I have really steep curves, very steep gradients, then if I shift two curves and add them, then what I get is this down at the bottom here. And this bottom curve, and you can see that there are these little plateaus that form, but also I have these regions of steep gradient, and those steep gradients, I have steep gradients and zero gradients. The zero gradients don't change when I add two functions together. And so what I can get is if I define a function that is the difference in the two plateaus, divided by the two interference regions, divided by the regions that don't change, the height of those regions that don't change, then I can get a very stable single parameter estimation. And using these techniques, by just looking at interference, for example, 2 modes from a target, I was able to resolve 2 targets 100 times better than the standard interference technique, and was able to get sub-millimeter resolution, even with waves that are meters in length. In fact, using these band-limited functions and these 72 centimeter cables is basically the thing I'm trying to resolve. What I'm doing is I'm changing the frequency, and what I see is I can actually resolve things 35,000 times smaller than the range resolution. And we can do this for multi-parameter estimation. And so I know this is kind of short, but I just want to say we've now been able to do 30 million times better than the standard. We're able to do 30 million times better than the standard resolution, and we've been able to do many parameter estimation, meaning we can look at many different depths and curvatures of surfaces. Okay, I know it's short and quick, but I want to keep to the time. So thank you. Questions? Rustem.
Yeah, I have a question. It
Yeah.
looks very similar to the ideas of chirp radar. Do you know about that? Something?
No.
No. The idea was just to make a chip when you send the pulse, which is chirped, because linearly chirped.
Yeah.
And then you receive this pulse and you make down chip in receiving system.
Yeah.
In this way, you very much shorten the.
Yeah, that's pulse compression. That's standard. That's the FMCW. And what you're doing is you're creating a CW. You're changing the frequency and time, and then you do chirped pulse compression.
Yeah. So your idea is different.
Yes.
Okay.
Yeah, but that's basically that's FMCW LiDAR. Yeah. Other questions?
I have one question. So,
Yeah.
Thank you for your talk. Can we improve standard resolution by introduction of polarization, degree of freedom?
That is a good question. I don't know. I have an answer on that right now.
Mm-hmm.
I think people probably use that. For example, when you do a matched filter, usually what happens is you do a single cycle and then switch a phase, for example, and then you create a signal with these randomly oriented phases, and then you create a filter that has the inverse of that randomly oriented set of phases, and then you're able to do these pulse compression techniques. I don't know about polarization, but I think you might be able to do the same thing with that as you do with changing phase. That's a good question. I just don't know.
Thank you.
Okay, I don't know your name at the top there. Yeah, go ahead.
Yeah. Did you try to estimate the tolerance to the noise of the signal? So I see that these beautiful pictures there should be very sensitive to signal to noise ratio.
Yes, they are. We wanted to focus on the effect initially, but we're now doing more signal to noise ratio. There were we did do, for example, this right here. We are doing noise estimates here on these curves, and it is very sensitive. It is very sensitive to noise, but we didn't do an extensive analysis. We are doing theory on that now. We just wanted to prove. So in all the previous definitions of range resolution, there is no definition associated with noise. It's simply C tau over 2. And so we wanted to show that you could do much better than C tau over 2, but obviously you're right. You need to do a noise analysis if you're going to do better than C tau over 2. And so that becomes critical.
So maybe the good application would be not only radar, but for example, a fiber reflectometry, where you have pretty strong reflected signal.
Yeah, and we've actually done a theory work now where we've showed that we could get 24 yoctosecond LiDAR range resolution. And if you're doing this with fibers, that you could get ultra high range resolution for LiDAR, but we were using a different technique than this. But you're absolutely right. And that one we did do a signal to noise ratio analysis on it. But that'll be for future works. I probably better stop it there and give it off to the next speaker. I want to be a good example here. So our next speaker will be Rustem. And let me just pull up here. So Rustem, can you share your talk?
I'm starting. Just remove your demonstration of screen.
Okay. And he's going to be speaking on nonlinear optics from the Kazan Technical Institute in Russia.
Do you see my screen?
Not yet.
Not yet. Okay. Something is wrong. You have to start again.
There we go. Okay, Rustem, I'll warn you at the 15-minute mark.
Okay, thank you.
Okay, thank you.
I would like to express my thanks to Olga for the kind invitation to present this talk. The title of my talk is Gamma Echo in Optical Domain. And I choose this title to pay tribute to a scientific group from Finland who first invented and experimentally implemented this idea with gamma photons. Okay. Few words from the very beginning. I have to pay attention to the optical transients induced by weak fields propagating in the thick resonant medium. I will discuss linear optics regime, which is valid for weak field, but I consider propagation them in a thick medium. I will first consider transient notation and free induction decay. As regards gamma echo, it is somehow analogous to photon echo by constructive interference of the field emitted by the excited dipoles. However, it's different from conventional photon echo since gamma echo appears due to interference with the incident field, while photon echo is generated when the incident field is off. This is experimental example of transient notation observed in optical cloud, dense cold optical cloud of potassium atoms in magneto-optical trap excited by step-switched laser. You see, if we had this laser detected without optical cloud, we had to just see the step function. But if we transmit it through the thick resonant medium containing resonant particles with homogeneously broadened narrow absorption lines, Then with increase of the optical thickness of the sample, the level where the intensity of the field drops goes down. And alpha L is just the product of the absorption coefficient and length of the sample. Also, you have to pay attention that with increase of the optical thickness, the decay rate of the field to this level also increases. This I will not discuss in detail this figure, but I give you another example of transient mutations and free induction decay observed in a cloud of rubidium atoms excited by long rectangular pulse, resonant pulse. You see, this is just pulse without absorber, and this is transmitted through the absorber. We see again optical transients, and it goes to almost zeros because optical density is quite high. And after switching off the resonant field, we see free induction decay, ringing of dipoles excited inside the cloud. These are also some zoom in to the free induction decay, to the transient notation and free induction decay. And about theory, which helps to understand this process and which gives idea how to observe other transients. And here I present results of my calculations published in 2012 of propagating of rectangular pulse through the resonant optical medium with large thickness. And you see that again, however, here I present the time dependence of the field amplitude, not intensity. And initially you see that after switch on of the pulse, we have almost no absorption. Then transient mutation is seen as fast decay to the level defined by the Beer's law. Then after switch off of the field, the free induction appears, which is the pulse with almost the same amplitude, the input pulse, but has an opposite sign. And how it is interpreted, that when the external field comes into the sample, it excites all the dipoles or resonant particles in the sample and experience the resonance scattering in forward direction. It forms a scattered field which propagates the same direction and has opposite phase. For the thick sample, the amplitude of the scattered field is almost equal to the amplitude of the incident field. Therefore, we have destructive interference. And when we this field develops during a particular time, and after developing to the full length of this vector, we have almost zero absorption, or absorption predicted by the Beer's law. And the thicker the sample, the faster this process takes place. And now about gamma echo. With a single gamma photons emitted by cobalt-57 nuclei with the energy 14.4 keV, and it was transmitted through the resonant absorber containing iron-57 nuclei having the resonant transition for this gamma quanta. Single gamma photon wave packet has a semi-exponential waveform. Shown this is just theoretical calculation from this paper. And when the scattered field is fully developed, the source experiences fast displacement on a half wavelength. Therefore, the emission field at this time changes phase by pi and starts to constructively interfere with the scattered field. We see the flash, the pulse. And the intensity, maximum intensity, which could be obtained here, is 4 times larger than the intensity of the incident field. And this is the experiment. This is the phase shift obtained by the absorber due to the induced by the displacement, which is caused by the electro-optical by piezoelectric transducer making a fast displacement of the source. And we see that before this displacement, we have a fast attenuation of the single photon wave packet. It means that at time approximately 200 nanoseconds, this scattered field is developed. And at this time, they apply the phase shift and they observe the gamma pulses. And plot B differs from plot C by what? By phase. For plot B, the phase shift is about 2.4 radians, which is smaller than pi. And for plot C, the phase shift is 8.5 radians, which is larger than 2 pi. And this is just application of this idea to optical domain. In this paper, I consider the propagation of the field through the thick resonant absorber with a narrow homogeneously broadened line width of particles. And I apply on periodically at these moments of time the phase shift to the incident field of rectangular shape. And it can be implemented by electro-optical modulator fed by rectangular voltages. And you see when phase changes to pi, the pulse appears. Then after some time, when it comes back to the value of 0 from pi, we have another pulse. In between, new scattered field with opposite phase develops, which results in destructive interference, reducing the field intensity to the low defined by the Beer's law. And what is interesting here, the field with a periodical change in phase, according to this picture, acquires the spectrum of this field changes from single line, narrow line, to the comp structure containing many spectral components separated by the frequency of the phase change. And the spectrum of this field actually broadens because in the case of gamma echo, we need this time. We cannot make distance between these pulses shorter, and therefore all the spectral components of the comp, which I showed you in this slide, interact with the absorber. Therefore, there is a fundamental limitation for increasing for shortening of the distance between pulses. And in this respect, this scheme is not very practical for application in optical telecommunication. This example of an experiment published in 2015 shows experimental observation of such a trend, which was showed in a previous slide. Probe laser is phase modulated and transmitted through the cloud of cold atoms, and periodically it experiences phase shift by pi, and each time when it happens, we observe the pulses. And these sample was quite optically thick. For this reason, the absorption line experiences thickness broadening, and the repetition rate which they would achieve was about 4 times shorter than decay time of the optical coherence of atoms. And now I propose to improve the scheme in the following way. I consider the same phase modulation of the incident field, but I take a phase shift which is 2 pi. And actually, this pulse sequence, I mean, the sequence of the phase shifts, produces also quite short pulses. And the figure below shows the zoom in the appearance of this pulse. By blue dotted line, I show the phase evolution, which evolves linearly. And you see that exactly when it crosses the value pi, we have a maximum of the pulse. Pulse starts to develop during the phase shift, so we can estimate the duration of the pulse as a duration of the step of the phase change. On the left side, I show the spectrum of the field experience such a phase shift. Quite well. This is the period of this pulse train, and this value is this is the window where the phase shift takes place, and the spectrum becomes quite broad. This is just the envelope of the spectrum. Each component of the spectrum is quite narrow, and I show only 5th, 10th, and 15th components. Actually, there are many spectral components, and they are quite well resolved. And this is example of such a phase change. It was published recently in 2017 by a group of Azana. And here, by available technique, he was capable to create a rectangular change of the phase. It's some kind of, they call it binary phase change, but the maximum phase shift was pi over 2. And what is interesting for me, that the frequency of the phase change is about 4.5 gigahertz. So it's a quite large frequency. And this is the spectrum of such a field. And you see that all the spectral components are quite well resolved. And in my idea, I propose to remove the central spectral component, which is well resolved. And it is not even necessary to make such a removal by filter consisting of resonant atoms. It is possible to do by available spectral filters, which I will not discuss here. But if you ask me, I will tell you the principle how they are built.
Rustem, 2 more minutes.
Okay, I am almost finishing. This sum mathematics. This is just spectrum of the field spectral components of the field whose phase change periodically according to this binary law. And this is the value of the central spectral component. And it doesn't change too much if the time during which the phase changes is much smaller than the period of the phase change. And if we remove this central component, which is written here, then the intensity will contain the interference of these two components. And you see very simple expression, which quite nicely describe the production of pulses. And if phase is 0, we have sign minus here, and we have a minimum of the transmission. Ideally, A is quite close to 1, so it's close to 0. And if phase is pi, then we have sum of these terms, and the intensity becomes 4 times larger than the intensity of the incident field. And this way allows to generate a sequence of pulses at desirable time. For example, we can do what? We can, at this moment of time, we can switch on this, change the phase by 2 pi, then next change back comes at another moment, which we need to transmit the information yes, and next time at this time, etc. So in this way we can excite the pulse at initially designed time slot. For example, in this time slot we have the signal, and at this time slot we have no. And just how it could work, we have a external cavity laser producing CW field, and this field is very well stabilized. It passes through electro-optical phase modulator, then through the programmable filter, which removes the central frequency component, and at output we will have this train of pulses. And conclusion. Well, in this method, I propose generation of pulses of controllable duration and time spacing with high stability, because all the elements in this picture do not produce a noise. Such a generator is easy to incorporate into optical and electronic circuits and synchronize with other control devices. And this method allows to obtain pulses with high contrast and does not introduce extra noise. And here, just interference allows to redistribute field energy between time slots with pulses and within pulses and dark windows. Thank you. I finished.
Thank you, Rustem. Questions?
No questions.
Any questions?
People are tired.
Okay, well, let's thank Rustem again. Thank you, Rustem. We will now have our next speaker, Yuri Kurochkin from Abu Dhabi, and he's going to be speaking on quantum communications.
Okay. Just one question. Do you see the screen? Oh, there is some. Okay. Yeah. Okay, there is some problem with the full screen demonstration, so I'll try to demonstrate it like this. I want to say thank you to Olga for the invitation, and I want to say thank you to my colleagues Rodrigo Piero, Jadip Singh and James Grieve, with whom we do this research. And we do it in Abu Dhabi in Technology Innovation Institute, which I have joined a little more than a year ago. This is a large research center, including different centers, different sub-centers, and one of them is a world-class quantum center. It has different groups, including quantum computation, quantum communication, and quantum sensing, and several groups of theory support. So I'm in quantum communication, and our focus is quantum key distribution and quantum random number generators. Today, I want to focus my talk on quantum random number generator results, because that's one of the most applied technologies in the overall like cloud of different quantum technologies. And first of all, let's see where we use random numbers. So there are three big directions: the Monte Carlo simulation, the cryptography, and gambling. And all of them have different requirements. So in gambling, like most funny, but most required, because people needs to believe that asks that random numbers are really, really perfect. But if you look at Monte Carlo simulation, for example, it requires uniform distribution, it requires a non-periodic structure, but it doesn't require unpredictability. So the predictable, the reproducible results are advantage of Monte Carlo simulation. At the same time, in cryptography, we require random numbers to be unpredictable. In principle, they can be periodic with large period because people don't use very much of this sequence. But uniform distribution, surprisingly, is not obligatory request because, for example, if we use as an initial seed something like 5 subsequent zeros, which or like 8 or like 128 subsequent zeros, which is in principle possible outcome of random number generator, but in terms of like complexity, it's considered to be a bad key, and it's not used, of course. And if you look at properties of different random number generators, the algorithmic one, pseudo-random numbers, physical random number generators, and quantum, we see that they have also different advantages. So algorithmic provides you pretty uniform distribution, but at the same time, they are predictable and they can have large period. The physical and quantum random number generators play on one field and they have very common properties. So if you want to like propose people quantum random number generators, it should have some advantages in front of physical random number generators. And physical random number generators, like on diode noise, they should be isolated from external factors, and the same applied for quantum random number generators. And if we look at like quantum nature is considered to be really, really unpredictable, but then we need to distinguish somehow which noise comes from classical source and which noise comes from quantum. And if you look at different types of quantum random number generators, let's say short noise, quantum based on balanced homodyne detector, it has impact of quantum noise and impact of classical electric noise of the system, of our amplifiers, of our digital analog to digital converters. And we should consider this effect. At the same time, the beam splitter with like classical choice, where photon goes, reflects or transmits, again, we cannot do it ideally 50-50. So there is a still classical effect which should be considered, and it should have some post-processing. And we should have very good estimation of this effect. And what about post-processing? For example, if we have an entropy source at the very beginning and generate some random numbers, first of all, we should estimate which amount of entropy from this, from initially generated, is really quantum. And then we apply hash function, which can be really, really good. For example, Toeplitz matrix is considered to be good. If it's randomly generated, it's considered to be good for Q and G. And then we apply epsilon factor because, of course, we have pure random gas and some advantage above this, and this epsilon above pure gas can be done arbitrarily small, but of course it cannot be done ideally zero. So we sacrifice some amount of random numbers to make it more and more unpredictable. And then we make, of course, some verification at the output, and that can be done by the final user. But for the final user, the quantum random number generator is a black box, even though the final user can open it and believe how it works. One of the big questions is there is a hash function, and a hash function is the algorithmic pseudo-random number generator. What is the difference between ordinary pseudo-random number generator? So there is difference, and the main difference is that an algorithmic pseudo-random number generators take small amount of initial entropy and generate large amount of random numbers. But in the hashing for physical or quantum random number generators, we take a large amount of initial entropy and then decrease this. We squeeze resulting output to have epsilon guessing. But then we need somehow to make like this idea convincing, and very important to make possible for final user to test and to understand the properties of initial entropy source. And three years ago, the group from Wrocław University in Poland proposed an idea of public randomness verification. And the idea is based on entanglement. So we can generate the state presented here. And if you can see, there are only 4 outputs, but 3 bits representation, because they are interconnected by XOR relationship. So that's the third bit is exclusive OR on the first 2 bits, and that allows you to have 3 bit strings and announce one of them, discard second, and use third as private secret. And like in public, in cloud, anybody can make a real public test of the random properties of initial entropy and say that yes, the hash function was applied correctly. Initially, the proposed idea was to use it even without hash function, but it requires you to have ideally equal coefficients between all 4 components, which is not really possible in physics, but we can try to do it. So we decided to make it an experiment. And I like quantum physics because you can do complicated things simple. So you can make entangled states by nonlinear processes, but at the same time, you can make entangled states with linear optics and post-selection. So you just take a coherent state, they use subsequent beam splitters, and at the output, you expect 4 coherent states. But then you require that you put 4 single photon detectors and require only one of them to click. So you post-select a state that initially you had only one photon, and you see that all properties of this state are behaved like entangled. There are a number of works, even with this sparse entanglement demonstration of Bell inequality. But here we do not focus on this. It's not fully device independent. That's just public verification. And we check there's a randomness properties, so we can equalize these states these outputs pretty well. We tune the energy of each pulse. That's 2 clicks are strongly suppressed compared to 1 click, and we also disregard them. And we see pretty good randomness tests outputs. But then we start to look at the system and ask ourselves, what can go wrong in this system. And we find out that the weakest point in the system are the single photon detectors, which are fast operating electronics devices, and they can degrade over time, or they can be affected, for example, by the power supply, even by 50 hertz effects. At the same time, beam splitters are pretty reliable and they vary much slower. So we decide to exclude the difference of the detectors and use only one single photon detector. So we recombine back all signals on the path selection. But to do this with just one detector, we replace 4 detectors with we replace path choice with the time window output, and then we can measure the time of arrival. We know that we have used a short laser pulse at the beginning. We use time tagger, and we can generate outputs using the same. So we know that even if our single photon detector will degrade on its efficiency, it will be applied simultaneously to all time windows, and it will demonstrate some slowly varying correlations. They will appear on much longer time periods and the time difference between pulses, which is on nanosecond scale. So we have a pretty good balanced situation. Of course, not ideal. That's why we need to apply post-processing, still need to apply this hash function. And we demonstrate that, yes, public verification is possible, and possible to demonstrate it with linear optics without nonlinear crystals. And but we require simple statistical analysis on site. So we need to check the balance between outputs, but all the rest complicated tests, the randomness tests, we can be done on cloud. So the device itself doesn't require high computational power. Thank you very much. And yeah, hope there will be
Thank you, Yuri. Questions? Well, I have a question for you. What about just putting a large beam so that it's relatively uniform across a single photon array of detectors?
Okay, so the problem with array of detectors is the same as the problem with 4 detectors. So as soon as you have 2 different devices which are operating at fast time at high frequency, they can be different, and their difference can vary pretty fast in time. Let's say 50 hertz induced from the network. So that's why we focus. We try to reduce the number of such elements to just one element, one detector. And if it will vary at some bandwidths, we put the constraints that this system is tolerant. Let's say that if there is 20 nanoseconds between pulse, if this system is tolerant to all variations which happens above, let's say, 100 nanosecond period.
Okay, thank you. Any other questions? Okay. Thank you, Yuri, and Alexei, you're next.
Yeah, I'm here.
Okay.
Do you guys see my screen?
Yes. Okay, so Alexei from Texas A&M will be speaking on optical frequency cones from quantum cascade lasers. Okay, turn the time over to you.
Yes. Thank you very much for the introduction. Of course, many thanks to Olga for invitation and organizing this meeting. So now I'm going to switch gears more towards lasers, and particularly quantum cascade lasers. Quantum cascade lasers, they are ordinary, at least they look and smell as ordinary quantum well semiconductor lasers, which is a $1 trillion industry, but in their heart is different kind of the optical transitions. The normal lasers operate due to interband transitions between, conduction valence band, recombination of electrons and holes. However, the quantum cascade lasers operate due to intersubband transitions between the quantized electron levels in the same, quantum wells. So essentially, you would need to create population inversion between those quantized electron levels. And they have sharp lines because, the same curvature of the band. They have very large dipole moments, and they are very tunable just by the shape of the quantum well. However, realistically, realistic materials, they more or less constrain operation of QCLs. It's just because of the conduction band offset to either mid-infrared region, because you can't get otherwise deep enough quantum wells, or to the terahertz region of hundreds of micrometers wavelengths. There is, of course, the phonon restraining band in the middle, which kind of absorbs everything. So, and of course, you could imagine their main application is in spectroscopy and imaging. They cover molecular fingerprint region. They are very powerful, so they have a lot of this kind of at least peaceful application. I'm not talking about anything else. So the main problem with QCLs is how to create population inversion, because the lifetime of an excited state is extremely short. It's limited not by the optical transition, but by the optical phonon emission. So relaxation occurs sideways, and you can't do much about it. It's just, the property of the material. So the characteristic lifetime of electrons in excited electron state is of the order of 1 picosecond. This means, to operate the lower laser state need to be depopulated even faster by resonant phonon emission or by resonant tunneling. So usually it's 10 times faster, about 0.1 picosecond, so extremely fast. And also the high performance laser should have these injector regions that adopt for electrical stability, and they create the Chirp superlattice, which creates reflection for electron wave packet in the upper laser state, and it creates the tunneling miniband for electrons in the lower laser states to facilitate the electron extraction. So they are pretty sophisticated but extremely robust and well-working devices. And of course, you can imagine you can have as many cascades as you want, as practically possible. So you can get up to 100 emitted photons per each injected electron. So very powerful, but that's not my main topic of my story. I'm talking about dynamical effects and multimode and coherence effects. And from that point of view, situation does not look good, because this extremely fast gain relaxation time means that the laser is essentially an overdamped oscillator. You can't have ultra-short pulse mod locking. So the relaxation times of your material are extremely fast as compared to anything related to photons. At least photon round trip time in the cavity or the general lifetime in the cavity. So from this dynamical point of view, they should be called class A laser, whereas all other solid state and diode lasers are class B, as you can see from this diagram on the right. So now, in order to facilitate multimode operation of any kind, you also need to introduce some nonlinearity. There are many kinds of nonlinearities possible, but it turns out that very unexpectedly, by far the most important nonlinearity which promotes nonlinear operation is just simply the saturation nonlinearity of the gain transition. Turns out to be the strongest and more or less the fastest. So, of course, as any semiconductor laser, QCL can have many modes. There could be many longitudinal modes in the Fabry-Perot cavity. There could be also transverse modes if the transverse area of the laser is large. And as you can imagine, different modes compete for gain, and if one mode eats away all the gain at the peaks of its field intensity, then another mode can start lasing at slightly shifted pattern. So this is called spectral hole burning, and that's main mechanism for multi-mode behavior in quantum cascade lasers. Now, in general, these modes don't have to be locked into any particular phase of frequency relationship. They are non-equidistant because of dispersion, and they have random phases. So it's not even a periodic process. However, they can be locked due to the same saturation or linearity of the gain medium. And that's very different from all other mode locking examples. In all other examples, let's say at least solid state lasers, the gain recovery time is very long, much longer than the round trip time. And when you introduce extra nonlinearity in the cavity, saturable absorber, then what happens is that the gain will stay below losses most of the time, except for the time and place where the pulse propagates. Only at this point, the gain will jump above losses because losses will be saturated, and you will create a narrow net window for the gain. So you will create ultra short pulses, then it will be strictly periodic process, and it will be looking like a frequency comp in the frequency domain. That's not going to work for quantum cascade lasers. Their gain recovery is extremely fast, and immediately after the pulse is gone, the gain will come back to its unsaturated position, and therefore you will just proliferate random pulsations and eventually your steady state operation. So again, what causes frequency and phase locking and formation of comps? It turns out that to a first approximation, just nonlinearity of the gain medium is enough, contrary to many things that we learn from the textbook, if this gain recovery time is extremely fast. In this case, you can adiabatically eliminate in first approximation the inversion and polarization in the medium. And then you will be left with equations for the modal amplitudes, basically cavity dispersion and loss, the modal gain, and also this phase-sensitive nonlinear mixing term, which is four-way mixing, again, in the first approximation. And then it turns out that this is enough to generate a comp, but very weird kind of a comp. There won't be any ultra-short pulses for sure. Let me first mention that the very first observation of this frequency comps was made in broad area quantum cascade lasers with many lateral or transverse modes. What happens in this case is that each transverse mode, it has its own comp of longitudinal modes, many of them, hundreds sometimes. So it's like superposition of three different comps. Comps is a bad word here. They're initially incoherent, but they start interacting due to nonlinear mixing, and eventually they can merge, completely synchronize into one comp. And that's what was observed in experiments and later shown in simulations and modeling. So the spectrum drastically simplifies, becomes like a single comp of longitudinal modes. The far field and near field patterns could be very weird. And in general, this kind of regime is not very well controllable. It's more like a sea of chaos, and there will be some islands of stability and synchronization as you would expect from any ensemble of a large number of nonlinear oscillators. So it is, of course, desirable to have it more predictable. And in 2012, there was a paper from Jerome Faye's group in ETH Zurich, which showed that even in high performance lasers with only one transverse mode, you can lock longitudinal mode by carefully engineering the dispersion in the waveguides. And of course, it would be much easier and better for application. So now back to my question, what kind of operation is this? Since it's frequency and phase locked, it has to be strictly periodic in time domain, right? However, you can immediately see that if the relaxation times of the gain medium are very fast, then so basically you can eliminate polarization and population inversion. Any amplitude modulation, let alone short pulses, will be completely suppressed, and the signal will be as close to frequency modulated as possible. So it is frequency which should be periodically modulated in such lasers, whereas intensity should stay in this limit, ideally constant. Actually, in this limit, the laser remains very old ideas from the 60s about how the laser operates. A kind of maximal emission principles, a little bit of anthropomorphizing the laser, but still, the laser feels urge to maximize energy extraction from the active medium. And you can easily see that it would require frequency modulation and no amplitude modulation. So if you do that, then you will get this funny laser. Recently, we have checked in a controllable way how this, it actually follows from variational principle in this case, how this maximum emission principle can be measured and established in quantum cascade laser when the periodicity, essentially the frequency distance between the teeth of the laser is small enough as compared to, or rather the repetition time is much larger than the gain relaxation. Then it's almost exactly FM operation. When, of course, it gets larger, hundreds of gigahertz, then it's no longer true. And speaking of how to make this separation between teeth larger, isn't it defined by the cavity round trip time? Well, yeah, but it turns out that you can operate a laser in the so-called harmonic frequency comb regime, where the separation between individual teeth in your comb could be 10 or even 100 times the cavity round trip frequency, which is extremely strange. So isolated, far distant modes are operating and nothing is in between. It's a very mysterious regime, and it is a comb which has been verified with very high accuracy. So indeed, it's frequency and phase lock with high accuracy. So what is going on here? That's certainly not class A laser dynamics, because the bit node is in sub-terahertz or even terahertz frequency. So it's certainly not a very long time and not a small frequency of beating. So something else is added here. Something else is actually coherent population pulsations, which is, again, leading, of course, to modulation of everything. They are tunable by optical injection. They are actually very interesting phenomena. You can even use it as a kind of transducer from optical regime to microwave or terahertz emission. For example, you can, with a scanning probe, you can see that there is a very strong pulsation of the current along the chip of the laser. And then if you put an antenna on top, you can basically pick it up and radiate it in a free space, for example, making a radio or TV. Unfortunately, it's hard to do it in terahertz. So these particular experiments were still in the microwave range. But in principle, potentially, you could use QCL as a terahertz communication device in this fashion. But back to the comps. So the mechanism of the harmonic comp is still unclear, I would say. The brute force time domain and space time domain simulation, they show that this regime exists, but it's metastable or very fragile to, the conditions of a laser. What happens is that if you consider instability of weak modes in the presence of very strong central mode, then indeed the gain, including population pulsations, will have this very distant wings. However, they are not narrow, they're extremely broad. So you would expect that actually many laser modes could be operating there, not necessarily harmonic, ideally harmonic spectrum. If you add more strong sidebands, then indeed you can suppress these intermediate modes and get something closer to the observed harmonic regime. But amazingly here, still, theoretically, this regime is more fragile than what experimentalists observe. Now let me, closing the end of my talk, to show you even more astonishing from my point of view operation regime of frequency comps in QCLs. Ring cavity QCLs. A ring cavity, you can operate it in unidirectional regime when the laser mode is just a running wave going running and round in only round and round in one direction in a cavity. So there is no spatial Hall burning, no standing wave structure. And therefore, you should not expect even multi-mode operation, let alone comps. And yet, experimentally, these lasers do show frequency comps. Moreover, the envelope looks closer to the ideal second square pulse, second square envelope. So what is going on here? Again, it's not completely clear, but I'm just want to show you some physical ideas. In this case, the prevailing idea is that the operation becomes closer to externally pumped Kerr nonlinearity micro resonators. So at least the spectrum looks very similar. However, of course, Kerr microresonators are externally pumped. They are not generators. And moreover, Kerr nonlinearity in QCLs is extremely small. So what makes this combo operation possible? That's what even makes multi-mode operation possible, let alone comps. So it's interesting. There was this recent paper that we published in collaboration with the Harvard group, Federico Capassa group, that it turns out that at least in some approximation, the operation, or rather the dynamics of these lasers is similar or could be described by complex Ginzburg-Landau equation, which has a characteristic Benjamin-Fair instability. The main factor of this instability is so-called line width enhancement factor. Well, it's simply
Let's say 2 minutes.
Oh, thank you. That's actually enough. So essentially what happens is that for very fast gain relaxation, this line width enhancement factor, it imitates Kerr non-linearity in the material, and it can trigger both multimode operation and also frequency comp operation. So there is multimode instability again similar to the one in complex Ginzburg-Landau equation. And then the nonlinearity takes over and creates a comp. At least that's the prevailing idea. The origin of this line width enhancement factor, which has been measured, but origin is clear, is again a matter of debate. So I'm not going too deeply into it because I have no time. But this kind of established much closer the connection between ring cavity quantum cascade lasers, so active devices, and passive Kerr nonlinearity powered ring microresonators, which are, of course, a very popular way of generating white light, continuum, frequency comps, etc. And moreover, you can even control the spectra and generate harmonic comps by introducing teeny tiny defects, basically cuts in this ring cavity lasers, which will promote certain pattern and suppress certain longitudinal modes. So, yeah, probably should mention that you can do similar things with terahertz quantum cascade lasers, as was shown in our recent collaboration with again the group from ETH Zurich, where the mechanism of this multimode behavior is probably the existence of several active transitions simultaneously, because it's very diagonal structure. So I probably don't have time for that. Probably just to, but you will stop me, right, when my 2 minutes is up. So far, I only talked about passive, self-starting comps, basically just mod locking occurring spontaneously. In principle, you could modulate a segment of your cavity actively with RF injection. And in this case, you don't need necessarily long gain recovery time. You can have active mod locked devices, but they don't perform as well so far. They require huge power of RF modulation if you modulate some subsegments. So in principle, it is possible. It shows picosecond pulses, which is also not fun. It does lead to very broad frequency comps. And it works slightly better in external cavity, as we showed a few years ago in collaboration with the Sheffield group. But yeah, I would say that it's more fun to have this passive mod locking in the form of frequency modulated or nearly frequency modulated frequency comps. So to summarize, surprisingly, I mean, this field of fundamental laser dynamics is such a well established and well routed, but still quantum cascade lasers continue bringing new surprising features to it. And it is the kind of area of research where in many cases experimental research is far ahead of theoretical. So there are still many mysterious features that, however, are very robust and well reproducible in the experiment. And usually it happens all the way around. Thank you.
Thank you, Alexei. Questions? Vitaly?
Alexei, are you saying that the temporal profile of this mysterious frequency modulated regime is just uniform field, or you still have many pulses profiles? What is the temporal profile?
Okay, so it looks like when the comb is dense, so every single longitudinal mode is generated. There are simply no competing short time scales competing with the gain relaxation. And the a laser output in time domain is very close to constant intensity and essentially the almost purely frequency modulated comp. The deviations may occur at very high power when the RNGH instability may kick in, and it will the spectrum becomes very strongly modulated. But normally for most of the operating range, that's the case. However, in harmonic comp regime, this is most certainly not true, because in this case, the bit node between neighboring modes is in the hundreds of gigahertz or even in terahertz range. And that certainly creates strong amplitude modulation. Now, if you go to ring cavity QCLs, nobody measured that. Actually, there are no detectors that could do that in the mid-infrared. But the popular point of view is that there could be curl-like solitons generated in ring cavity QCLs, because that's at least theoretically the natural development of this Benjamin Fair instability. So it could be even fancier, but I have not seen any experimental confirmation to that. Actually, it turns out it's extremely painful to do experimental measurements of supposed picosecond pulses, of sub-picosecond pulses in the mid-infrared range, especially when they go with such a high repetition rate.
Okay, thank you. It's still a mystery.
I would say...
You mentioned the possibility of active modulation by the radio frequency field. What is exactly the mechanism? Is it via Rabi modulation, Stark modulation of the level?
Yeah, actually, here is the thing. It's actually inefficient, because normally for QCL, when you bias it, like here in DC bias, well, you have gain. But when you apply the RF modulation, there will be no strong absorption at the, like, for example, in one position of the pulse. So it's not like you strongly modulate between gain and absorption. At best, you will get transparency region there. This is what's causing all these practical problems. Recently, Vien group had a very interesting design of this multiple quantum well, which does have absorption resonance at negative bias and gain at positive bias. And they did succeed in getting better quality amplitude modulated pulses and comps because of this bifunctional design. But in general, this requires a lot of effort. So for normal QCLs, it's not going to happen. This modulation will be bad.
Okay, thank you.
Okay, thank you, Alexei.
Thank you so much. Let me stop sharing.
Okay, Yuri Rostovtsev, you're next. You there?
Oh, yes, I'm here. Just 1 second. I will go into now sharing the screen. Just where this? Just 1 second. I need to find what I need to share, and I think here. Okay, it's can you see it? It seems like
okay.
And
turn the time over to you, Yuri.
Okay, so I would like to thank organizers and Olga Kocherovskaya to invite me to participate in this conference. And I'm going to talk about some kind of systems to gas detection. And in particular, this system is going to be developed similar to quantum sensors, which means that quantum kind of feature of the material will be very essential. So technically, what I'm going to say, and I'm going to say that, for example, quantum sensors in principle is very promising because they somehow to reach the limit, the physical limit of possible, implementation. And there are several already quantum sensors out there. So, and here we will try to develop something which will be like universal detector, universal sensor for gas medium. So because it's molecular detection, there are several kind of like transitions in the molecules, and I'm just kind of describe the logic why we choose exactly the region we would like to work on. And first of all, there are some electronics transitions which have like some optical transitions. There are some vibrational transitions, and all of them live in some kind of very different frequencies, and these different frequencies cannot be unified for, like, you cannot choose one frequency for all molecules. And then what we have these rotational frequencies, and rotational frequencies also unique because rotational frequency depends on the kind of like structure of the molecule, momentum of inertia, which is also unique, and all this transition between rotational frequency is unique. So, but somehow in these rotational levels, they're rich enough in order to apply external field, and you can some kind of create some splitting due to magnetic field or electric field. And then you can kind of like create some, depending on the external field, you can create some frequency, and this frequency will be the same for all molecules, but it will depend on the external frequency, on the external fields. So what I mean is, like, for example, if you have similar, like if you have NMR or APR where you have a spin transitions and you apply an external field, and this external field is actually create some frequency, some transition and some frequency transition, and when you flip spins, you can detect actually the spins. Similarly, you can use Stark effect, and in our case, we would like to use actually magnetic or electric field in order to produce some split in the molecules, and namely in this rotational structure of molecules, which is in some sense maybe limitation for detection, but on the other hand, practically, if you have some molecules you would like to detect, they usually have actually rotational structure. Also, our limitations come to the, we would like first to start with the molecules which has already electric dipole, and this is of course not always the case if you would like to detect like general molecules. So if you have this dipole and you have, like, for example, a molecule, then you can have rotational levels, and then if you apply electric field, you can somehow see what is happening over there. In the strong field, because of the electric dipole, you actually align molecules, and in this case, this molecules becomes like simple harmonic oscillator, and they would have some transition between them according to the simple harmonic oscillator. But this frequency will be determined by the dipole moment and moment of inertia of the molecule, which is two parameters, which is technically select actually determine molecule very precisely. And the good news is that we don't really need these strong fields. A weak alignment is actually enough. So the whole idea is just to use some splitting between molecular level, and the whole splitting is determined by the actual experimental part. It depends what kind of frequency is available for experimentalists. Any frequency in some sense would be available, and currently we are doing experiment is in very low frequency range, but even with this low frequency range, we can see some kind of like confirmation of the effect. So there are two ways you can imagine that. First of all, you apply electric field, or you can apply magnetic field, or you can apply electric field for detection or magnetic field for detection. Depending on this, you can use this impedance meter, and this impedance meter will determine the presence of the molecules, and once it's determined the presence of the molecules, you can know that there are this molecule. So this is somehow this kind of like the idea that you can do it, and there are some whatever this theoretical approach, you can see that you can write all these equations, and these equations will show all this what is needed to be shown. And the interesting part is, of course, that if you're using some DC field, and this is not exactly DC field, but it's adiabatic field, And this adiabatic field, when it comes through the resonance, it actually can cause the swapping of the population. And this swapping of population somehow changing, it can actually enhance the sensitivity of the technique. And then you can also estimate what is the noise in the system, and using the noise of the system, you can estimate what is the minimum density, of molecules you can actually detect. And the whole idea is that once you changing, when you sweep this frequency, this is like this linear change of the electric field, and there is this change of sweeping of the population of the molecule. But please to know that this population of molecules is really close, because the frequency separation is really small, and it is so small that it's practically the same population at room temperature. And there is a strong change of the phase associated with this. And if you now differentiate the change of the phase, then you can see this resonance, and this narrow resonance, its position will determine what kind of molecules we have. Based on this, we can somehow estimate what are these molecules, whatever list of molecules we are making, and then with dipole moments and the parameters of the rotational spectrum, you can see what kind of DC electric field you need and what is the minimal density which you can actually determine. And the whole idea, actually, the attractiveness of this idea is actually is that if you have some kind of these resonances should be actually narrow, because if they are narrow, then you can distinguish one molecule from another. And if you have a gas mixture, then somehow all this possible gas, at least theoretically, can be determined. So, but for example, and this is a big challenge. So this is some kind of this chirp effect, how it works, that if you have some field, and now if you tune either frequency of transition or the frequency of this electric field, then you can see that because of this, the dipole transition, there is no crossing. And if you look what happens to this levels with adiabatic transformation, if you go from like blue or red detuning, you can see that the line looks like this plus or minus levels. They look like either ground states or the excited states. And if you switch the transition through the resonance, then ground states becomes excited states, and all population is transferred over there. And this somehow can approach the theoretical limit of detection, because usually if you just use a probe field, then this probe field can maximum it can absorb is 50%, but with this coherent adiabatic control of the population, you can somehow reach that every photon can be actually absorbed. So, and this is another kind of figure showing the same thing, that if you use this linear chirp, you can see the swapping of the population. So the whole idea would be nice if this lines is going to be narrow, because under the conditions what this experimentalists would like to work, they would like to have work at the room temperature and at the pressure, atmospheric pressure, and nevertheless still have a narrow line, which is if you estimate. And this is kind of preliminary experiment. So we use some material, some oxide, and if you put some like molecules and no molecules, then you can see that in the electric field, this molecules is aligned on this material, and because they kind of like they have a dipole moment, they change their position, and you can see some features in this impedance picture. Then, and this impedance picture is similar to some kind of trivial, some kind of simple simulations what we can have, and some kind of, this is if you have these molecules, and then if you, this is how it looks like, and then this is what this impedance meter gives you. And somehow if you look on this picture, so in generally you can see that there is some effect of the from the molecule, and the only problem over here is you can see that there is nothing even close to the narrow resonance. So the whole kind of idea is to find out this narrow resonance, which means that we should select right actually transition and the right structure of levels in order to find it. And the idea of now to find the narrow resonance is actually to look what is going to happen when the molecule in the electric field. When the molecule is in electric field, everyone like knows that somehow there is this Stark effect, and the Stark effect somehow split levels, but it leaves some levels not split it at all. So there is this, I will show later that actually this is really close to this dark resonances, because if you have some field and you have, let's say, the molecule with this momentum of with momentum 1, then there are 4 levels. And if you have 4 levels, then there should be some bright states and there should be 2 dark states. And now these 2 dark states, they will be degenerate, and this turns out to be for Z polarized electric field. It will be in the Z direction, so this Z level will move, but these 2 levels with plus minus 1, they will actually move together. Because they're actually moving together, which means that the transition between them is not actually a factor of this broadening by collisions. And that's kind of like general idea, and the rest is just some kind of what we show is that if you have some fields, and these fields, what it does, it's leave some 2 states always not touch. They do always degenerate, and whatever states we have, depending on the polarization of the field, you have some parallel, whatever parallel means, and whatever orthogonal means, whatever field you use, you will have some splitting, Stark splitting between them. And if you have magnetic field, then you can see that there is a splitting between these levels because they correspond. These levels 1.1, for example, it is m equals 0. It will be not influenced by magnetic field. But this two crossing levels, they correspond with plus minus, and in magnetic field they will split and they will create some transition. Unfortunately, this transition is forbidden for dipole transition. So in that regard, you have to use some additional field, and this additional field should be some part of the electric field, which is not parallel to the magnetic field. So in this case, you can see that there is a transition, and this transition will be allowed, and this allowed transition is not going to be subject of the collisional broadening. So. And now this is kind of like this simulation. So if you have some transition, if you have some polarization, and you drive this polarization at a resonance, then you can see this yellow line always showing that you will, if you have no broadening, then this amplitude of polarization will just grow. And if you have some collisions, then these collisions, what these collisions going to do? They're going to produce some shift of frequencies, and this shift of frequencies will be put the system out of resonance, and the growth of polarization will be much slower, and will cause the decay, etc., etc. So this is the collisions coming, this broadening coming this from dipole interaction, for example, and then for example. There are 2 cases which we need to compare, and this case, one case is this m equals 0 transition with this j equals 0 transition when actually you have always some splitting. This splitting happens all the time, and this transition will be always broadened. And if you increase the collisions rate, then actually this broadening will take effect. Meanwhile, all these 2 dark states, two states like m equals 1 plus minus 1, for example, they will be always in the electric field move together, and because they always moving together, then actually the broadening will be actually decreasing if you increase the number of collisions. So technically, this is similar. This is exactly what we're looking for. We just need, out of all possible transitions, we have to work on these transitions, and that provide all of this. Narrow lines, and these narrow lines can be demonstrated, and these lines will show exactly what kind of molecule we have. And now it is just maybe some connections with yes. Oh, okay. So I think I'm exactly, because this is, like I so far explained the idea, now some connection in order for people knowing quantum optics, how to easy to understand what I was talking about. So if, for example, you have these 4 levels, and this is like a states J equals 1 of the molecule and J equals 0 of molecules, and you apply any electric field, what is going to happen is that you will be always have these bright states, the only states coupled to the transition, and there will be 2 states depending on the polarization. It will be either plus minus 1, or if the field is not exactly in the z direction, it is also equivalent to the transformation of the coordinate system. There will be always 2 dark states, and these 2 dark states is not going to be splitted by this field. And now, if you somehow apply additional field to split it, you can actually organize this transition, and this transition will be not the subject for these collisions. And in order to some kind of to show you, there is some kind of even experimental demonstration of similar effect. I just realized that it is happening because there is this feature of the AIT, and this is like big bird's big view, which is always was a surprise. It seems like over here, whatever theory you're using, you have some kind of parabolic dependence. And how come it is very sharp and this type of behavior, then what I just considered with molecule, some kind of, I have I don't know if anybody interested in AIT, but somehow this big behavior of the AIT, it looks like that once you have these 2 levels, bright state and dark states, and this dark state is given by this equation, then if you consider what would happen with collisions, if collisions is exactly on the dark states, because of this in this magnetic field, you can see that it's decoupled from the electric field. So with all this combination of the dipole moments, it actually gives you that there is no actually collisions this stark shift of this level, and there will be no actual collisional broadening. And this collisional broadening is exactly we seen when we approach to the AIT as this big feature. So now its conclusion that technically we somehow, by choosing wisely the transitions, we can find out even in the nasty atmospheric condition some transition which is actually narrow, and we can somehow using this narrow transition in order to develop quantum sensors, which is possible to make a detection of the mixture of gases. Thank you very much for your attention.
Okay, thank you, Yuri. Questions for Yuri? Vitaly?
Yuri, you mentioned that you can achieve 100% probability of absorption of photon. What did you mean by that? Is it really a quantum sensor? Just you can use the probe with just 1 quantum level of intensity, or what?
Well, this is like theoretically. Theoretically, it's true, but somehow at this moment, I can only draw attention. Oh, wait, anyway, you remember probably somewhere this view graphs that technically, because of this, here. So theoretically, when you're using this chirp, then somehow out of all probe which you have, you will absorb exactly 1 photon. Even so in that sense, you somehow theoretically, if you're able to distinguish absorption of 1 photon, so it will be your ultimate detection limit. So it's not related to some kind of probability less than 50%, what is using for transmission spectroscopy. And in some sense, I can say that somehow we are thinking, is it possible somehow to do it with a single photon? But at this moment, I don't know answer on this question, although theoretically, as you can see, there is a promise for that, because there is a simple physics related to that actually single photon can be actually absorbed. There are several special cases which you need to provide in order to do that, but some kind of using this, like cavities, and you somehow can create condition when actually happens. It's not simple, of course, but on the other hand, it is really promising to have detection with a single photon.
So if you send Fock state with say 4 photons, one will be absorbed and 3 will be detected. This kind of measurements.
Right, and 3 will be yes.
Okay, it sounds great.
Yeah, if you can distinguish this, if you somehow can distinguish that, then it, like in the area we are working. No, we are thinking some kind of about this, but somehow in the area we are working, we have really low frequencies. With these low frequencies, like 10, 100 megahertz, it's really but if, for example, there are some collaborators which can some kind of work in higher frequencies, like terahertz, then or infrared, then there somehow it would be more possible, I would say.
Yes, I see. Thank you.
Yeah.
Any other questions? Okay, I'd like to thank all the speakers and, Olga, you have a question. Olga? Okay, I saw her hand go up. Anyway, want to thank all the speakers and also thank Olga for putting the session together. Okay, thank you all. Olga, did you have anything more?
Thank you, John. Thank you so much.
What you'd like to say?
That's it for today. I have a question I will discuss later with Yuri because the session is over. It's okay. So thank you again and see you tomorrow morning again.
Thank you.
Thank you.
Bye.
Юр. Уже сейчас.
Where is Olga? Okay. Sorry, I disconnected, and but Olga is gone. Okay. Thank you. Bye.